Yeah, is it recording? Woo!
Yeah.
Welcome, Precalc C. We're taping class for no reason. We have a new unit that we are starting today. Cool? All right. And this unit will feel very different, because it is different, from all the other things that you have done so far in high school math, at least. This is a kind of unit which is going to go on for like 4 or 5 weeks on discrete mathematics, which, very loosely speaking, is the branch of math that focuses on like finite objects and like finite structures. Although even that's a little bit not the best definition. So like whereas most of the things you've done for the past 1.5 years have been like, you know, continuous like functions and stuff like that. Now we're going to talk about like integers. All right. All right. First, a story. There is a story. It is surely false. It is, what's the word? Apocryphal. It involves Gauss, Friedrich Gauss. Is that his first name? I believe so. One of the like smartest like 2 people ever in the history of the world. And where is he? Carl Friedrich. Friedrich is his middle name. And he was very good at arithmetic, as you might imagine, being like one of the top 2 greatest mathematicians of all time. And he was also annoying his 5th grade teacher, as you could also imagine, somewhere up in like, you know, the hills of Austria or whatever. And the teacher said, Gauss, like, go in the corner and add up all the numbers from 1 to 100. And Gauss looked at him and said, it is 5,050. Whoa, how did he do it? Some of you may have heard the story before, so like, don't answer if you know. Can I just tell you? Or maybe you tell me. So, yeah, pairing, exactly. Woo! So we go, we take 1 plus 2 plus 3 plus, and we go all the way up to the end, which is like 99, you know, plus 100. And we're not as smart as Gauss, so we're gonna like write it all out and like use letters and stuff. Let's call this S, S being the thing that I'm looking for, yeah? Okay, and now there's this ingenious move where you write all those same numbers but backwards. Oh. Yeah. Okay, so I sort of wrote all the numbers from 1 to 100, called that S, wrote all the numbers backwards, but by aligning it this way, what can we do? Add. Oh, that's brilliant. Because when we add, we get 101. Here we get also 101. And here we also get 101. Okay, this is not a coincidence. This is because these numbers are going up by 1 each time, and these numbers are going down by 1 each time, so like duh. Okay, they're going to stay, the sum is going to stay constant. And if I do that, then I get twice the thing that I'm looking for. And then how many of these 101s are there?
100.
100 of them, because there were 100 numbers I was adding, right? So I have 100 times 101, or I'll just say 100 of them. And so it must be that twice the thing I want is 100 times 101. And so the thing I want is 50 times 101. And that's like 50 times 100 plus 50 times 1. So we get the answer. All right. Cool. Cool. Raise your hand if you've seen this before. Like you heard this whole, whoa, like almost all of you. Wow, cool. All right, good. Let's take it up a small notch. And let's do it now in general. Okay, in general, so now I don't want to stop at 100, I want to go to like n. Okay, so let's do 1 plus 2 plus 3 plus, but now I have to be a little bit more smooth. Then this, like the second to last number would be like n minus 1, and the last one will be n. Okay, so what I want is a formula for that. Let's just call it S. And, well, okay, you just do the exact same thing, right? You write all the numbers backwards, so n minus 1, this is n minus 2, 2. So the logic is exactly the same. Now there's just a sort of a smidgen of algebra, because we're trying to do it in general. And now, if I add columns, 1 plus n is N plus 1, and 2 plus n minus 1 is n plus 1, and 3 and n minus 2 is also n plus 1. And these are just all gonna be n plus 1 because, and the logic is the same as before, these numbers each time are going up by 1, but these numbers are each going down by 1, so their sum is like staying constant. Cool?
Cool.
Okay, this, if you add it all up, is twice the thing we're looking for. And what is, how many of these n plus 1s are there? N of them, yeah. So there are n of them. And so it seems that if I have n of these n plus 1s, then I get twice what I want. And so, so the thing I want is n times n plus 1 over 2. And this is a nice little formula, which it sounds like more than half of you have seen this formula already. It's like comes up in like middle school or math team or whatever all the time. It's a formula for the sum of the first n positive integers. Cool. Oh, these have a name, these numbers? They're called the triangular numbers. Let's do that now too. Can you see clearly over here?
I'll move back.
Let's see like in the way. Or not. Okay, good. So like, if the sum of the first 1 numbers is like 1, the sum of the first 2 numbers is 1 and 2. The sum of the first 3 numbers is 1 and 2 and 3. And the sum of the first 4 numbers is 1 and 2 and 3 and 4. And so they make kind of like triangles, right? So they're called the triangular numbers. So we say like T1 is 1, T2 is 3, T3 is 6, T4 is 10, and these things come up. Does anyone see what I'm doing? All right, so that is awesome. Oh, wait, before we leave this, how do you feel about this proof? Good? I got a thumb up, I got a solid, I got another thumbs up, I got everyone saying thumbs up. Alright, basically okay with it. Anyone see any like potential shaky parts? Yeah, how about everyone talk at once?
Well, if there's an odd number of things, but like it is not a positive integer.
Oh, if
Okay, they're all positive integers, so that's not the issue.
if
If you have an odd number of terms, it still works just fine, right? Because, yeah. Yeah, oh, no one, this is awesome. Yeah, maybe no one has any problems. We can all just go home. No, I think there are some like little problems, not with the result, but with the proof. I'm just not really sure like what's going on in here with these like dots. These dots make me a little nervous. Like, you know, if you're like in the middle of a wedding ceremony and in the middle of the vows, someone says, and you know, more of the same, you know, kind of blah, 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 and then cuts to the end. Would you be a little bit concerned about that? Yeah. Or if you had some kind of, you know, contract for like a mortgage on a house or whatever, and you know, you got like page 1 was all these like legal terms, and page 2, and then pages like 3 through 17 were just like, and you know, just some of that stuff, dot.
I mean,
okay.
That's basically what happens when you read the terms and conditions of everything.
That's true. But they are there in theory. So, yeah, so the point is, these dots, there's the potential here, you know, for maybe someone's trying to trick me. Because what you're really doing when you're throwing in these dots is you're saying, come on, you know, it just kind of keeps doing what it's been doing, you know, it's just more of the same. So some might object to that as being like really like a proof at all. It seems very kind of casual. So there is a way to do this sort of more formally in a kind of a tighter manner, and we're going to do that in a couple weeks. All right. Right. Oh, wait, not even the last thing yet, because there's also another thing. You could just leave it like this, or you could also use this thing called sigma notation, which I think you are like mildly familiar with already. And you have this Greek letter sigma, and it sort of represents the sum of a bunch of things. And you just go, okay, start counting when I is 1, and the thing you should be adding is just I. And stop when you get to n. So the way you should interpret this, it says, set I equal to 1, and add 1, 2, and then now increment I to be 2 now, add that, and just like keep on adding and stop when you get to n. So this is another way of expressing this thing that we proved, which says if you take the sum of all things of the form I, where I starts at 1, goes up by 1 every time, and ends at n, then that's n and n point. Alright, how are we doing? Alright, this was just like fun, happy intro. Let's like start the unit for real now. So the first thing that we should talk about are sequences. Alright, what is a sequence? I'll just say for today at least that a sequence is just like an infinite list. It's kind of just an infinite list. Alright, let's do an example. Example 3, 5, 7, ... What comes next?
Minus 1.
No, like what's the next number?
9.
9. Or 11. Or
Something else.
look like literally anything. It's a trick. The ... dots are obscuring the truth. Because who knows what this list could be? It could be, you might have guessed right, that we were listing the odds. In which case this sequence would be 3, 5, 7, 9, 11, etc. But it was also possible that maybe we were listing the odd primes. In which case it was supposed to go 3, 5, 7, 11, 13, 17, you know. And it was also possible that we were listing like, you know, my favorite numbers from some old movie or something, which happened to be 3, 5, 7, 10, and then just an infinite sequence of ones after that. It's an awesome movie. Okay, so in reality, this ... thing is kind of crap, right? Because who knows, if you just say ... I don't know, how am I supposed to know what you're thinking? So what sounds like what we need is some way of talking about, and the pattern continues. Like some algebra, or notation, I guess is what we need. Alright, and we do have such a notation. If I want to describe this sequence in which we're listing out the odds, I can tell you that like the first number is 3, and the second number is 5, and the third number is 7, etc. Sorry, computer scientists, but we start counting with 1. That's just what we do. There's no conversation about it. We're doing it. The first term is 3, the second term is 5, that's what we're doing. Okay, so if that's the case, then what is the nth term? Maybe you can just tell from just like common sense, guess and check. Who knows? Bridget?
2n plus 1.
I think he's right. Yeah, I think he's just like right about that, right? Yeah. But n is 1, it works, and n is 2, it works, it's good enough. Okay, good. Alright, so I have this notation that's like wonderful. What else? Oh, there are some famous sequences. I've introduced one famous sequence already, the sequence of triangular numbers. I'll introduce another famous sequence. It's called the Fibonacci sequence.
I didn't know that.
How many lines are in this? Yeah, I think it's spelled like this,
It's like
maybe. Okay, it sounds like you guys have probably already heard it, so here it goes. It goes 1, 1, 2, 3, 5, and in general, I get my next number by adding the two previous numbers, right? So this is like 8, 13, 21, So okay, that's kind of exciting. Well, how can we explain to someone what exactly this Fibonacci sequence is with our notation? We can just kind of do it, right? You have to tell me that the first term is 1. You also have to tell me that the second term is 1. But then I can get a formula. So what is the formula for the nth term if n is greater than 2? All the hands are up. All the hands. Yeah, what we got?
A is equal to a n minus 1 plus a n minus 2.
So this is a recursively defined sequence in which I'm telling you that the formula for the nth term, starting at term 3, is just the sum of the two previous terms. All right, everyone cool with that? All right, good. All right, so that was all like kind of just still warm up. Let's go to the most simple kind of sequences that there are, arithmetic sequences. Is this thing supposed to? Yeah, that's kind of in frame. All right, what is an arithmetic sequence? Well, it's just a sequence where you go up by the same amount each time, right? So here, we'll just start with an example. We have 5, and then 8, and then 11. What are we doing? Adding 3. So la 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 la. And what are we sort of doing? Well, each time I'm adding 3. So it's like, up 3, up 3. Okay, and good. All right, so there are 2 ways to describe, also, it's arithmetic, it's like an adjective, right? Everyone say arithmetic.
Aromatic.
No, that's a different word. All right, well, I can think of 2 ways to talk about this. I can do this recursively, and I can do it explicitly. So let's talk about these 2 different ways. What would it mean to define this sequence recursively? Well, now, Valentina, what do we do?
So you define each term with respect to the term before it.
Yeah.
So in this case, it would be like an equals an minus 1 plus 3.
Yeah. Okay, and then there's one more thing we have to do, otherwise we haven't specified.
Define a1. So a1.
Ta-da! This is a way of specifying this sequence, or defining the sequence, or describing it, whatever you want to say. The first term, I'm being told that the first term is 5, and I'm being told that every subsequent term, I should write when n is greater than 1, is the previous term plus 3. Cool? Okay. But I think it is also possible in this simple sort of situation to define it explicitly. And what I mean by that is, now you just give me a formula for the nth term as a function of n. Anyone want to just go for it? By just doing some common sense? Sujay really wants to. Sujay.
2 plus 3n.
Yeah, that's probably right, yeah? 2 plus 3n? Yeah.
Yes.
Yeah, how do you get that? Anyone want to do it a little bit more? Anyone want to outline their thinking a little bit more? Or possibly Sujay himself. Sujay.
So we know that a of 1 equals 5, and so we need to find what a of 0 is, and we know that it's incrementing by 3 each time, so we just subtract 3 from a of 1, and we can get a of 0, and so then a of 0 plus.
Yeah, that works. Another way of thinking about it is without that extra step. Yeah.
So the first difference of this is a constant, so that means it's a linear function.
Sure.
So then it's going to be in the form y equals mx plus b.
Yeah, sure. Wait. Stop. Good. Cutting you guys off. All right. So wait. I think this maybe the simple way of thinking about this is, the first term is 5. Fact. So what does every term look like? Well, the first term is 5. The next term is just 5 plus 3. The next term is 5 plus 3 plus 3. The next term is 5 plus 3 plus 3 plus 3, etc. So every term is just 5 plus a bunch of 3's. How many 3's? If I am on the nth term, how many times have I multiplied by 3?
N minus 1.
Not n times.
N minus 1.
N minus 1 times, yeah. So this is the same as what Sujay got, but it's a little bit more just written sort of directly from the kind of definition. Good. And actually, we can kind of do this sort of in general, because the best way to think about an arithmetic sequence is it's a sequence in which the difference between a term and the previous term is constant. If you give me a sequence and that sequence looks like like A, B, C, D, E, etc. And if you tell me that this is arithmetic, then the best definition of arithmetic is that if you take the difference between a term and the previous term, it's always the same. So that B minus A has to be the same as C minus B, has to be the same as D minus C, and etc. Cool? Say cool.
Cool.
Okay, so if the difference is common, we actually have a name for this. We call it, the common difference. And the common difference in an arithmetic sequence is sort of the amount that I'm adding by each time. And often we call that, but we use the letter D for that. And so what does a kind of a generic arithmetic sequence look like? It starts with the first term, A, and then the next term is A plus D, and then the next term is A plus 2D, etc. And by the time I'm on the nth term, what does it look like? How many times have I added D? N minus 1 times, if this is the nth term. Yeah? In the second term, I've added D once. When I'm in the third term, I've added D twice, etc. Okay, so what that means is that this generic arithmetic sequence can be given an explicit formula. The nth term is just the first term plus a whole bunch of D's, specifically n minus 1 of them. Good? Alright, so all of that was pretty chill. Now comes a hard thing. And there are going to be 4 of you who know this already, so be quiet about it. I want to add these guys up. I want a formula for what happens when I add up 5 plus 8 plus 11 plus 14, etc. And I eventually get to the nth term. And what does the nth term look like of this sum?
5 plus 3 and
5 plus, how many times have I added 3? N minus 1 times. Alright, so suppose I want to add all these up. Figure it out. Go. Anyone got any ideas? Anyone have ideas that hasn't seen this before?
Not done yet.
What's happening to your eye?
Yes, Brooklyn, can I have? Oh, I thought you-
No, I was just volunteering.
What?
Did you see my note?
Yeah.
Alright, you can ask you.
Oh. I want to volunteer on election day.
Election day? Election day? Yeah. I'll tell you. No, just 2 hour shift. Okay.
Okay, wait, said we're recording a video. Start say hi.
Why are we recording a video?
That's a long story. Alright, good. What should we do? Who has an idea? Yeah, what should we do?
So we know that we're adding like the 5 n times, and then we know that we're doing like we're adding the 3, 0 plus 1. Plus
Wait, this is a lot of talking. Can I get the big picture in like 5 words? Give me the big picture of what we should do.
So we should add the 5 just automatically, and then the 3 we should use the Gaussian technique to figure out how many samples we're having.
Okay, I heard one good thing from her sentence, which is, let's just do the Gauss thing, man. That Gauss thing seems like a great thing. When you want to add up a whole bunch of numbers, it's like, great. So can we just do the Gauss thing?
Yeah.
Wait, I think we can just do the Gauss thing.
Be careful, yeah.
No, I don't think we have, well, we always have to be careful because there are dangers out there. Like, you know. But I think we're okay. If what I want is 5 plus 8 plus 7 plus 3, can I think, Valentina, you're doing something which is cool, but I think it's more complicated than it needs to be. Can I just straight up, like, do the Gauss thing?
You can.
What number should I put here?
5 plus n minus 1, 3.
5 plus n minus 1, 3. What number should I put here underneath the 8?
5 plus n minus 2, 3.
Ooh, it looks like Adam got the word to be careful and decided to do correct algebra. Yeah, here we're now going like backwards, and now what's going to be the last term?
5.
5. Okay, so I think I can just do the Gauss thing. And if I do the Gauss thing, okay, it's a little bit more complicated than before, but what do we get?
7 plus 3 n.
Yeah, let's just like keep it not simplified. It's going to be 10 plus
Negative 3.
n minus 1 times 3. So I'm just going to leave it like that.
And then 13.
Okay. How about the next one?
13
plus n
plus
minus 2,
n
3.
minus 2.
Wait, did something go wrong?
No.
You just
Yeah,
did-
you didn't factor out the -1. Negative
Oh, I
1
see what
times
you guys
6,
are
that's
trying to
why.
tell me to do. No, wait. Oh yeah, this is kind of confusing. Wait, can you just take it on faith? What's this next one going to be?
13.
Same thing.
Wait, no, now I agree with all you guys. I see what you're doing. You want me to like
Just
simplify this and
simplify
stuff,
it.
right? Yeah, okay. So yeah, you're all right. I was being dumb. So yeah, because this gets minus 3, right? So it's actually like 7 plus 3n.
7 plus 3.
Yeah. That's like better. So this is 7 plus 3n. And now if I add 8 to this, now what do I get?
13 minus 6 is 7.
Plus 3.
So it's 13
Yeah.
minus 6, which is, it's again 7 plus 3n.
Goodness.
And that's not a surprise, right? Because after all, to get from 5 to 8, it went up 3.
Yeah.
Duh. And to get from this number to this number, I went
3.
down 3. So it makes sense that the columns are all going to be the same. Okay, let's skip to the end. What happens when I add these two?
7 plus 3n.
And I'm also going to get 7 plus 3n. How many of these n's are there?
N.
Minus 1.
N of them.
1, 10.
And so I think I just win, right?
Yeah.
Twice the thing I want is just going to be 7 plus 3n times n. And so s is just going to be 7 plus 3n times n over 2. Okay, who followed all this? Basically everyone. All right, good. All right, I've never done it this way before. That was kind of easy and satisfying because you came up with it yourself. All right, now let's do it in general. So in general, what I now want is the formula. So what? The formula for the sum of the first n terms of a generic arithmetic sequence. Okay, and what do I need to know? What things are gonna like appear in this formula?
A
So I'll just write like in terms of.
and
She says you have to tell me what the first term is. Let's call that A. You also have to tell me what the common difference is. Those two numbers characterize the sequence. And you also have to tell me n, how far out to go. Okay, so I want a big formula which will tell me, which will have A's in it, D's in it, and N's in it, which will tell me the formula for the sum of all the things. And it's basically just what we already did, right? Go.
A is the first one.
So I'm going to write this all out nice and pretty, because what does the first term look like?
A.
A. And then the next term,
A plus B.
what's D?
S equals to A plus.
What's 2?
A plus.
No, I'll skip, I'll do the second to last term just for fun.
A plus N minus 1.
Wait, and
No,
minus
N
2.
sorry.
Minus 2, yeah.
And then A plus N minus 1.
Yeah. And this is the nth term.
And then you will.
I already know this. We can help them
Yes. Oh, I don't know. I'm just gonna like. Alright. So now for the fourth time today, I'm gonna do the Gauss thing, and oh no, this is what happened. Oh yeah. Sorry.
Why are you doing the A plus and minus 2?
Oh no, I just got bored.
Okay. I mean, sure.
Okay, let's add. What happens when I add A to A plus n minus 1d?
2A.
2A plus n minus 1d. And what happens when I add A plus d to A plus n minus 2d?
Same thing. 2A.
Yeah, I'm also going to get 2A plus, this is n minus 1, but then there's like one more. So it's like n